Hello everyone. I am Mohammed Adil of Engineering Physics, BTech third year. In this presentation, I'll be covering Hall effect, which is one of the topic in my applied instrumentation course. So let's have a quick overview of the presentation. So in this presentation, first of all, we'll be looking at introduction, in which I'll talk about what is Hall effect and other stuff. And after that, we'll be covering the principle behind working of the Hall effect, and then we'll cover one of the most important part of the Hall effect, and that is Hall coefficient. And then moving on, we'll be looking at some of the important applications, like what are the sensors and transducers in which the Hall effect can be utilized, and then we'll look at the advantages and limitations of using Hall effect in the sensors. And after that, in the end, I'll be giving the references which help me made this slide. And so basically, Hall effect was discovered by Edwin Hall in the year 1879. So what he discovered that when a current carrying conductor or semiconductor is placed perpendicularly to a magnetic field, voltage is generated that could be measured at right angles to the current path. So basically what it means that whenever you apply a magnetic field perpendicular to the current direction, there is a transverse potential difference generated across the conductor. That transverse potential difference is known as Hall voltage, and this phenomena is called as Hall effect. So basically the principle behind it is that whenever you place a moving charge carrier inside an electromagnetic field, it feels a force because of that field, and that force is perpendicular to the direction of both the fields. And after that, we'll be covering some of the important applications of it, like how we can use it to find the magnetic field, and also we can use it to characterize the material, like what kind of material are we using for Hall effect as such. And at the end, we'll be looking at some of the advantages and limitations. So basically, the now we are going to cover the principle behind the working of Hall effect. So whenever you place a charge carrying conductor, and it has got some speed or velocity v, and if we place it in a electromagnetic field, then it will feel two kind of forces. One is the electric force and the second is magnetic force. So electric force will be given by the q times e, and the magnetic force will be given by the cross product of v and v, and it will be equal to q into v cross b. So whenever these two forces are present together, it is termed as Lorentz force, and the equation will be given as F is equals to Q into E plus V cross B. Now this is a vector equation. So if we extend this equation to all three coordinates, all three directions, so we get these three equations for Fx, Fy, and Fz. Now, depending upon what coordinate or axis we choose for the direction of current and magnetic field, we'll get to use one of these equations. Okay, now the magnetic force, electric force calculation is really simple, and the magnetic force calculation can be done by using the right hand rule or the vector product. So basically, it is a rule in which if you let the fingers of your right hand to point in the direction of its speed or velocity, and you orient your palm of your hand so that as you curl your fingers, you can sweep them over to the direction of magnetic field. All right. So your thumb points in the direction of vector product v cross b. So that's how we get the vector product v cross b. Now, if the q is positive, that is the charge carrier is an electron or hole. For the if q is positive, the charge carrier will be hole, and in that case, this vector product direction will be direction of force. But if the charge carrier is negative, then the direction of force will be opposite to the direction of vector product. So that's how we can calculate the Lorentz force. Okay, so now we'll be covering the Hall coefficient, which is one of the most important part of the Hall effect. So basically, it can be used for to find the various physical quantities like mobility, conductivity, etc. And it can also be used for the characterization of materials. All right, so the Hall coefficient is basically is the ratio of the induced voltage and to the product of magnetic field strength and current density. So we'll be looking at the Hall coefficient for two cases, for metal and for semiconductor. In case of simple metal, we have only one type of carrier, that will be electron, and for that we can write the Lorentz force equation as F is equals to Q into E plus V cross B. Now we intend to find the steady state condition. In the steady state, the net force on the charge carrier has to be zero. It will be because the electric field generated by the Hall voltage VH will balance out the force because of the magnetic field. So both of these forces will balance out and we'll get the net result as zero. So on applying that condition in one of the three equations that we got earlier, we'll get the result Ey minus Bx is equals to zero. So after further manipulations on this equation, we get the Hall coefficient, which is defined as RH is equals to Ey divided by Jx into B. Here Ey is the Hall field, electric field produced by the Hall voltage Vh, and Jx is the current density, and B is the magnetic field. Now putting in the values where we have got the dimension of this metal slab W, T and B, and on L, W, T and L, and on using these dimensions we can make some manipulation and finally we'll get the result RH is equals to 1 by N. So we can see that it directly depends on the charge carrier density. Okay, so now in the case of semiconductor, the derivation is not so simple because we have got there two types of charge carriers, both holes and electrons. So in that case, after derivations and some manipulations, we get the result RH is equals to P into mu h square minus N into mu n square divided by E into P mu h plus N mu n to the whole square. Here mu h and mu n are the mobilities of the hole and electrons respectively. Okay, so these are the Hall coefficient for the two cases. Now this Hall coefficient can be used to determine what type of semiconductor we have. So what happens is that whenever the Hall coefficient comes out to be negative, we can see that our majority charge carriers will be electrons, and from there we can conclude that our semiconductor is an n-type semiconductor. And whenever our Hall coefficient comes out to be positive, we can see that our majority carriers will be holes, and from there we can conclude that our semiconductor is an p-type semiconductor. Okay, now we'll be okay. Now we will be looking at some of the applications of the Hall effect. So we can use the Hall effect technology, and because of its application of contactless magnetic sensing, it provides exceptional value and reliability. And because of this, we can use it to manufacture various sensors and transducers. So one of the major application of Hall effect is to measure the magnetic field, and it can also be used to create magnetic field sensing elements, and which can also characterize the materials as we have seen earlier. And it can also be used to create proximity detectors, and it can also be used to measure speeds. Also there is one of the popular example is the magnetometer. So basically magnetometer, one of the popular example of magnetometer will be a compass, so which is used to measure the direction of ambient magnetic field. So it uses the Hall effect, and also we can also use Hall effect for the position and level sensing. Okay, so the application of Hall effect in the sensors and transducers have got very many advantages and limitations. So the advantages include like because Hall effect sensors do not have any contact with neighboring mechanical parts, so this makes these sensors strong and sensitive enough to detect any kinds of movement. And these sensors do not wear over time, so because of that they can maintain their quality over time, and can also be called as virtually unlimited use. And they can also be used for high speed operations, and they can also detect zero speeds, and they are highly reliable. And whenever they are packed, they can be very immune to dust, air, and water, whereas some sensors like capacitive sensors may get triggered by dust. Now we'll look at some of the limitations. So the limitations include, like, because the Hall effect works on the magnetic field. So whenever there is some external magnetic field present, then it can interfere with our results and can give us biased results. And these are also sensitive to temperature because the resistance of the material or metals or semiconductor changes with temperature. So the sensors which utilize the Hall effect will be obviously sensitive to temperature, and sometimes they also give non-linear response to magnetic field. So these are the references from where I have made the slide. These are some Wikipedia sources, and there are some websites from where I have taken some of these images shown earlier. So that's all. This was my presentation, and I hope I was able to deliver on the topic. And thank you everyone for your patience.